This video is about the homologous series haloalkanes, where we're going to be talking about what they are, how to name them, and then we'll be going through the reactions of monohalo alkanes. So haloalkanes are alkanes that have some of the hydrogens replaced by halogens. They can be referred to as haloalkanes, sometimes they'll be referred to as alkyl halides. You can have as many different halogens substituted onto the molecules. So for example, that one on the left, we see that it is ethane. It's got one chlorine on it, so it's called chloroethane. We've got two bromines on that molecule on the right. It's been drawn in skeletal formula. So they are both on carbon number 2. So it's 2,2-dibromopentane. So the numbering and naming system is very similar to a branched alkane, and we'll go over that naming system. So each halogen on a chain needs its own number to show its position. When you're naming the branches, the halogen or the halide branches, all you do is take the name of the halogen and turn the INE into an O. So bromine becomes bromo, fluorine becomes fluoro, etc. You've got to remember that this is different to when halogens are bonded on a transition metal complex, where you change their name from bromine to bromido. It's just an O when it comes to organic molecules, so there is a difference. If you have more than one halogen, you need to put them in alphabetical order, or it's recommended you put them in alphabetical order. So bromo before chloro, before fluoro, and finally you would have iodo. So here we have 3 examples. If you take your time to name these molecules. So that first one is going to be, it's based on methane, it's going to be trifluoromethane. The next one on the top right, well, there's one bromine molecule on it. The smallest number carbon it's on would be carbon 2 within that chain of 4, so that would be 2-bromobutane. And finally, that molecule got 5 carbons, so it's going to be pentane. We have got 2 different halogens. We've got bromine and we've got chlorine. Remember, putting them alphabetically, bromine is going to come first, so bromo, then chloro. And we want the numbers to be as small as possible, so it's going to end up being 3-bromo, 2-chloropentane. Now, monohalo alkanes are the main types of alkanes that you're going to be dealing with in synthesis reactions. These contain only one halogen on their system. And like alcohols, they can be primary, secondary, or tertiary. So a primary haloalkane, the X represents the halogen. If the halogen is on a carbon that only has one or no other carbons bonded to it, it would be described as a primary haloalkane. If the halogen is on a carbon with 2 carbons bonded to it, it is a secondary haloalkane. And if it has 3 carbons bonded to it, it is a tertiary haloalkane. You need to be able to identify whether they are primary, secondary, or tertiary, because just like alcohols, they do have slightly different reactivities. And this will come into play, particularly when we're looking at mechanisms for reactions. So next, we're going to be looking at the reactions of our monohalo alkanes. So the first type of reaction is called an elimination reaction. Now, elimination reactions go from monohalo alkanes to alkenes. You do need to know the reaction conditions and the mechanism by which this occurs. The mechanism will be on a different video. It's not shown in this because this is just an overview. All the mechanisms will have their own individual videos, so do look that out. So here, in our elimination reaction, we do require hydroxide ions to be present. And what happens is the hydroxide ion removes a hydrogen, and then you end up losing the halogen as well. So you end up forming a carbon-carbon double bond. You get water from the hydroxide ion and the hydrogen that's been removed from your haloalkane, and you get the halide ion removed as well. Now the conditions, what's put in bold, You need to reflux your haloalkane with potassium or sodium hydroxide, and it must be dissolved in ethanol. If you use sodium hydroxide dissolved in water or potassium hydroxide dissolved in water, you will get a different reaction. So this one is really important. It must be dissolved in ethanol, and a shortened way of saying that is ethanolic potassium or sodium hydroxide, as long as you can explain what the chemical and what the solvent is. And as I said, it will not work if you do it in water. In fact, you'll get a completely different reaction occurring. The products are an alkene, a halide ion, and water. Now, because of the position that a halogen might have, sometimes there are two possible products which can result in the formation of isomers. So for example, here we've got 2-bromobutane. We can remove hydrogen from the left-hand side of the bromine or from the right-hand side of the bromine, which will result in either forming but2-ene or but1-ene, depending on the particular hydrogen that has been removed. The second type of reaction that haloalkanes can do are known as nucleophilic substitution reactions. Now, nucleophile is any molecule or species or ion that is attracted to positive or delta positive charges. Typically, nucleophiles themselves are negative ions, or molecules like water or ammonia that have a lone pair of electrons. In a nucleophilic substitution reaction, your nucleophile with its negative charge is going to attack the carbon bonded to your halogen, and it's going to replace the halogen. There are two different mechanisms for this, called nucleophilic substitution type 1 and type 2, and you will learn about those again and those mechanisms in a different video. But a nucleophile replacing a halogen on the alkane chain. Nucleophiles are attracted to positive parts of molecules, and a carbon-halogen bond is polar, so you will be attacking the carbon bonded to the halogen. And this will be done through heterolytic fission, so the reaction involves ions. So in general, you will have a negative ion reacting with your monohalo alkane to produce a new molecule and a halide ion. There's a few different types of this. The first one is doing the reaction with potassium or sodium hydroxide dissolved in water. So remember, elimination reaction with potassium or sodium hydroxide in ethanol. To do a nucleophilic substitution reaction, it is sodium or potassium hydroxide dissolved in water. And what this does is it will turn your haloalkane into an alcohol. So the hydroxide ion replaces the halogen to form an alcohol, and you'll get the halide ion. And you will typically do a reflux reaction in order for this to happen. Reflux meaning you're heating it with a condenser directly attached vertically onto the flask so that you can keep the reaction at a hot temperature for very, very long periods of time without losing solvent. The second type of substitution reaction is a reaction with something called an alcoholic alkoxide. Now, an alkoxide is any alcohol group with the hydrogen of the hydroxide group removed, resulting in that hydroxyl group being an O negative ion. So methanol will form methoxide ions and the negative charges on the oxygen. Ethanol will form ethoxide. Propanol will form propoxide, etc. Now, how do you turn an alcohol into an alkoxide? Well, you react the alcohol with sodium or potassium. That sodium or potassium will remove the hydrogen, and you will be left with your alkoxide dissolved in whatever alcohol you had. That's why it's called an alcoholic alkoxide, because you will end up with methoxide ions dissolved in methanol, ethoxide ions dissolved in ethanol, etc. So here's examples of that. Sodium reacting with ethanol to form sodium ethoxide and hydrogen. And as I said, because you'll always have excess alcohol, the alkoxide will be dissolved in whatever alcohol you started with. And what's going to happen is the alkoxide is just going to replace the halogen, and the molecule you're going to get is called an ether. We will look at ethers in more detail. You just need to know this is how they're made. So here we have our alkoxide reacting with our halide. We replace the bromine in this reaction with that entire OCH3 group to produce the bromide ion, and that molecule is an ether. And ethers are really important solvents when it comes to processes like recrystallization, which is a purification technique. So again, the substitution, all you do is take the ion that you had and replace the halogen with that ion. The final type of substitution reaction is reacting haloalkanes with cyanides. So cyanides, they must be dissolved in ethanol for this reaction to work. And so ethanolic cyanides means they've been dissolved in ethanol, and it doesn't matter if it's potassium or sodium. Cyanide is C triple bond N. So what happens is that the cyanide ion always attacks through the carbon side, not through the nitrogen side. So you'll be adding on a CN group, not an NC group. And it forms nitriles, and nitriles are really important because a nitrile can be turned into a carboxylic acid. If you ever see over the course of a reaction the length of a molecule increasing by one carbon atom, the only reaction at advanced higher that can extend or make a chain longer by one carbon is by doing a nitrile formation. So in this reaction, we have our haloalkane, we have our cyanide group, which is dissolved in ethanol, and the final molecule is called a nitrile, and we get our halide ion again. So that has been our going through of the two main types of reaction that haloalkanes, monohaloalkanes can do. That is the elimination reaction. There will be a video on the mechanism for that reaction, and I will also have a few videos on nucleophilic substitution reactions because their mechanisms will always be asked, and there's a lot of information you need to know about when the two different types of mechanism might be used. So please watch up the follow-up video on nucleophilic substitution reactions.